Good? Okay. Hi, I'm Michel. I'm a fifth-year grad student at MIT, and I'll be presenting semantics of integrating and differentiating singularities. Work with my phenomenal collaborators Wonyeol and Hongseok, who I think are here. Yeah. All right, so consider the program 1 over x. We might ask what happens at x equals 0. And we get the famous divide by 0 error. And 1 over x is an example of a singular function, which is a partial function such that at one or more points, the left and or right limit diverge. So what if we take the integral of a singular function? We might ask, is the integral well defined? And the answer is no. And the reason is the way that you count area is by making these little rectangles. And if you draw a little rectangle around 0, it'll be unbounded, both below and above, right? So we're not going to settle for that, right? That's, you know, we can do something here. So what we're going to do is we're going to take an epsilon ball away, and we're going to say, hey, at least in this case, we can see the negative and the positive part cancel, right? So we should get 0 for every epsilon. And then we can take the limit as epsilon goes to 0. And this actually defines something called the Cauchy principal value integral, which is a singular integral. And it's defined exactly like this and is 0. All right, so this is a singular integral. And now we're going to take a look at automatic differentiation. So automatic differentiation automatically computes the derivative of a function. And it produces efficient derivative code because it preserves program structure. And there are these widely used libraries for automatic differentiation. And we can look at what standard automatic differentiation does for singular functions, and we'll get the same divide by 0 error at 0. All right, so now we're going to change this problem a little bit. We're going to add this parameter s in the denominator, and we're going to take the derivative of this integral with respect to s. And we'll get this result, right? OK. So we might ask again, is this well defined? And of course, the answer is no, right? You have infinite area in the shaded region, so it's not going to be well defined. But we're not going to settle for that. So instead, we're going to define something called the Hadamard finite part integral. And it's defined with limits sort of like the Cauchy principal value integral, except you have this lovely thing where you subtract this like 2 over epsilon term, which is sort of like getting rid of the infinity. You just kind of take only the finite part, get rid of the infinite part. OK, so one thing to note here is that the derivative of the Cauchy principal value integral is not equal to the Cauchy principal value integral of the derivative. But it is equal to the Hadamard finite part integral. All right, so it might seem a little bit crazy, right? All these weird different types of integrals. But it actually fits into a more general theoretical framework, which is called distribution theory. And informally, a distribution is a generalized function that's closed under limits and generalized derivatives. So we could take the limit of this sequence to get this Cauchy principal value distribution. And then we can take the generalized derivative to get the minus Hadamard finite part distribution. And because this commutes, we can go the other way, take the sequence of derivatives, and get the Hadamard finite part distribution, right? So this is a more general framework, and it's actually not all ad hoc. All right, so you might ask, why does all of this matter, right? And the answer is really singular integrals are like integrals or derivatives in that they're modeling tools. And so their value is defined by how useful they are at modeling things. So they're useful for modeling problems in signal processing, aerodynamics, and mechanical engineering. And a lot of these problems have a setup where you have some parameters, you have some loss that says how good your output is, and you do some gradient-based optimization. All right, so let's dig into this aerodynamics example. And in this setup, you have a wing, and to make your plane fly, you need a lift, right? And the way you can model this is you can slice the wing, right? So this little teardrop shape is a slice across the wing. And the goal here will be to calculate something called the circulation density, which relates to the lift, and it says basically how is the wind spinning at a particular point. And you can model this problem with a singular integral, this Cauchy principal value integral. And the unknown is this gamma in the numerator. And the other parameters are these physical parameters. And one way to solve this problem is with these physically informed neural networks, where we approximate gamma with a neural network, gamma tilde theta. And then we have a loss that's basically for a bunch of u-naughts, we're going to take the difference between the left-hand side and the right-hand side squared, so that at the minimum of the loss, the equality holds. All right, so just a little bit of story. So we were working on these problems with singular integrals, and we were trying to write some formalism. And we had some trouble with the math literature, getting something to the level of rigor that we wanted. So we ended up putting a fair amount of work into building up the theoretical foundation. And I think there are some, at least results we couldn't find in other places. So, and this presentation also only uses like the tools of calculus. It should be accessible. And then once we put the math foundation in place, we define the first semantics of a differentiable, or of a programming language with singular integration. It also is differentiable. And we solve some problems in science and engineering. All right, so let's look at some code for how to implement this in our language SingularFlow. The main sort of features to highlight, you have finite iteration, you have singular integration, and you have automatic differentiation. So now you might wonder, how do we run this integral, right? And so remember how the negative and the positive parts canceled out. So the idea behind the sampling algorithm is you take a sample from the positive part and you reflect it across the singularity. So they kind of cancel out. It's an algorithm to estimate that. And then you might ask, what happens when we run this code? Well, you have loss that converges. And if you were to do something like Monte Carlo integration on this problem, you would get a bad answer. And then you can look at the final circulation density in this problem, and you can see it matches by hand math approximation you can do pretty closely, which means that it's doing something sane. Now you can, okay, so we've solved this problem, and you can also apply the same technique to different shapes of airfoils, right? Different airfoil designs. And this sort of technique can also be used for solving inverse problems, like find the wing shape that will have the desired amount of lift, right? Okay, so now I'm going to dig into the PL. We'll be pretty quick here. So expressions denote smooth functions, and programs denote a smooth map from context to context, right? So the denotation of this assignment statement just updates x with the denotation of e. And for integration, the key takeaways are that you have multiple notions of integration, right? So you can denote a regular integral, a Cauchy principal value integral, or a Hadamard finite part integral. And the key sort of technical result that you need to make the semantics work out, in particular to make sequential composition work out, is to have the result that the integral of this smooth function in the numerator, right, g, is smooth, right? So you end up with a smooth semantics, so you're closed. And the paper extends this to include if statements and finite loops, which adds a lot of fun complexity, right? Okay, so that's the denotational semantics of this subset of the language. And we can go on to the operational semantics. And the idea here is you take in a context, a derivative context, which starts off as like a directional derivative, and an expression, or an assignment statement. And you update x, and you update x in the derivative, right? And you can do the same thing for this integration primitive. And the key takeaways here are that you have separate estimates of the integral and its derivative. And maybe a non-trivial choice that we made and that we show is produces correct results, is to reuse these samples. So just to reiterate, we had this result earlier that the derivative of the Cauchy principal value integral is equal to the Hadamard finite part integral, but it's not equal to just differentiating the sampler. So this sort of motivates doing, it's not as easy as writing your sampler and having AD take the wheel. All right, so you can see the paper for the full semantics, operational semantics, and a proof that that the operational semantics is an unbiased and consistent estimate of the denotational semantics. And then now just going back to the contributions, right? So we've talked about a little bit about the math, a bit about the formalism, and now we're going to talk about a few more applications. So we implement all of these applications in a little JAX library. We extend JAX with custom derivative, and the actual core implementation is just 100 lines or so of code to do that singular integration and to get the derivative correct. And now we're going to look at this Hilbert transform. So the Hilbert transform is much like the Fourier transform. It's a fundamental primitive in signal processing. And it's defined by this singular integral of a function. And we can just compare ground truth to ours, and the takeaway is they're equal. And we can note that standard Monte Carlo integration doesn't work well. And interestingly, Mathematica has support for principal value integrals and correctly computes the answers in this case, which I was excited to see. And then we can take the derivative. So this is also a useful quantity in signal processing. And again, we can see that ground truth and ours are equivalent. And if we just took the derivative of the Cauchy principal value, we get an answer that's like orders of magnitude wrong. And if we just do Monte Carlo integration, we get an answer that's also orders of magnitude wrong. And interestingly, if we take a look at Mathematica, it doesn't have a powerful enough symbolic solver to compute answers in these two cases. And it doesn't have a numerical solver out of the box. So we do a quick performance comparison. And the main takeaway is if you use JIT, right, the implementation is compatible with JITting, you get comparable performance. And if you don't, it's slower because there's stuff that the JIT compiler is able to optimize away that isn't optimized. All right. Now we're going to look at these crack propagation problems. So the idea is you have some material, we'll say like concrete, and it has a little crack under some force. And you might ask, how would that crack propagate? Right? So what is the crack displacement? And it turns out you can model this problem with a singular integral equation. So we have this Cauchy principal value and integral, this unknown sigma, another unknown sigma, and then the right-hand side, which is determined by the physical parameters. And we're going to use the same physically informed neural network approach to solve it. Right? You take the difference of the two, you approximate sigma with a sigma tilde theta neural network, and you find that the test loss converges and that the crack displacement that you get quite closely matches the ground truth, which you can laboriously calculate. And then we can also look at a 2D crack propagation problem. And this one has a Hadamard finite part integral in it. It's another singular integral equation. We can go through the same process and see that the loss converges, and you get a reasonable answer. So now I'm going to quickly talk about some related work. So there's these classic sort of math papers by Cauchy and Hadamard. There's the seminal work by Gelfand and Shilov. It's a big textbook on distribution theory that covers not these singular integrals with parameters in them, but singular integral operators. And then there are these numerics papers, one that has this symmetric sampling idea around the singularity, and a number of papers that study these finite part integrals In particular, Monegato's 2009 paper. It's really great. I really like it. And of course, this work draws from a lot of PL work on the semantics of probabilistic programming languages and automatic differentiation with discontinuities. So to talk about some future work, there are these 3D singularities that come up in computer graphics. I really like both of these papers. The first one handles singularities by sort of thresholding. So saying if you took a sample and you got a value that was too big, just throw it away and don't look over there, right? And it works fine, but I believe, and I think the authors believe, that there's some opportunity to more accurately model this problem. And another one is this beautiful paper on the Kelvin transform, where you take a simulation of a PDE on an infinite domain, use the Kelvin transform to map it to a simulation on a finite domain with a singularity in it. You by hand handle that singularity, and then you solve the problem, right? So I think there's an opportunity here to automate this singularity handling. And also for both of these, there's an opportunity to do automatic differentiation, right? So if you can take the derivatives through these singular integrals, you can start solving inverse problems as well. So there's a lot of future work in this direction for the PL community, handling multiple singularities, more general singularities, nested integration, multivariate integration, more expressive control flow, support for higher order functions and recursion in the semantics. So in conclusion, we have the first language formalization for AD with singular integrals. There's a big need for more language features and more generality. And there are lots of exciting applications in PDE solvers, writing better PDE solvers with more automation, and to problems in computer graphics. And the open source implementation is here. And I'd like to thank Wonyeol and Hongseok again for all their help on the project. Thank you.
Thank you, Jesse. And we have time for a question. Yeah, for us.
Okay, good. Thank you for the talk. Very cool work. So one thing I noticed was the Monte Carlo variance was quite low in your experiments. Have you found areas where you're using Monte Carlo integration, right? Sampling to estimate the integrals. Have you found areas where the variance is too high? Maybe there's numerical instability, where you might need maybe a better estimator for the expectation rather than the naive Monte Carlo, using like importance sampling, or what are some opportunities there? Or are these all basically low dimensional problems where the uniform 0-1 generator that you showed is good enough? Thank you.
Right, so this is a great question. So there's a bunch of numerics work on making different samplers. We're using a sampler that's not the lowest variance. There are definitely opportunities there. And we show sort of 2 bits, like base 10, 2 bits of precision in our tables. But there are techniques that get, I think in King's book on the Hilbert transform, he gets like 10. So there's definitely a lot of room to be more precise in this problem. And we're also looking at single dimensional problems where doing like quadrature methods will probably significantly increase performance when they're tailored to the integrand. So I think there's a lot of opportunities there. And then in higher dimensions, I'm sure there's a huge amount of work that could be done there of making better samplers.